In the previous video, I introduced you to several equations that we can use to solve problems involving objects moving with a constant acceleration. So the basic idea, illustrated in this figure, we have a car moving with a constant acceleration. At some earlier time, we have kinematic variables time zero, position zero, velocity zero. And then at the later time, we have kinematic variables time one, x1, velocity one. The delta t, or change in time between these two events, is time one minus time zero. So in any of the formulas here, when you see a delta t, that means t1 minus t0. Anyways, the three equations I introduced you to in the previous video were these three here. In this video, we're going to solve an example problem using these equations. And to guide us through solving the problem, we're going to use this handout here, which is available in the module introduction. We have a car driving down the freeway, and the car is initially traveling 45 miles per hour, but then the car gets to this sign which changes the speed limit to 65 miles per hour. So the driver decides to accelerate, and the driver accelerates at 3 meters per second. We're assuming he's getting faster here. The question is, how much time does it take the car to reach 65 miles per hour? And then the second part is, what distance is traveled in this time? So let's start going through the problem using the handout. Step one says, draw a clear sketch illustrating the problem. So we have the beginnings of a sketch, but we will add on to the sketch as we go through the problem. 2, coordinate system. All right, I already did that. We have an x-axis pointing to the right. The coordinate system should have a clearly marked origin. So I'm going to go in and put the origin at the position of the 65 mile per hour sign where the action begins. Step 3, identify and number the moments of interest. So in this problem, there are just 2 moments of interest. Our first moment of interest is where the driver sees that 65 mile per hour sign and decides to begin accelerating. So let's call this moment 0. This is where the acceleration begins. And then the second moment of interest would be where the driver reaches 65 miles per hour. Let's call that moment of interest 1. Okay, now step 4. At each moment of interest, write down the appropriate kinematic variables. Option A, constant velocity problem. No, this is not a constant velocity problem. Option B, constant acceleration problem. This is a constant acceleration problem. So what does it say? It says, next to each moment of interest, write down symbols to denote time, position, and velocity. Write the acceleration off to the side. So let's do that. At moment 0, we're going to put in time 0, position 0, velocity 0. And then at moment 1, we're going to put in time 1, position 1, velocity 1. Okay, and we can put the acceleration. Normally I put the acceleration down here, although I haven't quite left myself enough room, so maybe I'll squeeze it in there. Okay, that was step 4. Step 5, for those kinematic variables whose values are known, write the values of the kinematic variables on the diagram next to the variables. So here, I would invite you to pause the video, carefully read the problem again, and then for any of these quantities where the values are known, go ahead and fill those into the figure. Then you can rejoin the video. Okay. Now, we don't actually know what time it is when the driver passes the 65 miles per hour sign, but it seems convenient to just start the process at time 0, or at time 0 equals 0. So let's put that in. We put the origin at the 65 miles per hour sign. So the position here is 0, and the velocity was given as 45 miles per hour. Now, we don't really like dealing with funky units like miles and hours, so we're going to need to do a unit conversion, but we'll get to that later. Okay, so then time 1, the time at which the car achieves 65 miles per hour, we don't know that. That's one of the things the problem is asking for. so we'll leave that blank. We don't know what the position here is, but we do know that the velocity would be 65 miles per hour. So let's go ahead and put that in. And it is also given that the acceleration is 3 meters per second per second. So I'm going to try and squeeze that in. So 3.00 meters per second squared. Okay, now we have this annoying issue of the unit conversions. Generally, when we are working a physics problem, we don't like to have miles as our distance unit. We would rather have meters. We don't like to have hours as our time unit. We would rather have seconds. So we're going to convert these velocities from miles per hour to meters per second. So I'm going to do that here using the procedure I demonstrated for you in the first module. So we have 45 miles per hour equals 45 miles per hour. So we put in the conversion factors. I want to cancel out mile. A mile is 1,609 meters. I want to cancel hour. An hour is 3,600 seconds. And when you crunch this into your calculator, I hope you get 20.11 meters per second. So I'm going to take that and put that into the figure. Again, I seem to have made this figure a little crowded. And 65 miles per hour, I'm going to skip the conversion, but I'd encourage you to make sure that you know how to do this. That turns out to be 29.05 meters per second. Okay, so let's look at the questions. Part A, how much time does it take the car to reach 65 miles per hour? So we are looking for time 1. So what I'd like you to try is to go through the 3 equations here and see if there are any of those equations where everything is known except for time 1. If you can find an equation where everything is known except for time 1, then solve symbolically for time 1, right? And then after solving symbolically for time 1, put in the numerical values along with units, and then compute the numerical value for the answer along with the unit for the answer. I'd like to give a hint before you try that on your own, though. Just remember that anytime you see a delta t in one of these equations, you can replace that delta t with t1 minus t0. Okay, now go ahead and give this a shot on your own before rejoining the video. Okay, so here's how we do part A. Let's look at equation 2 there. I'm going to write equation 2 as v1 equals v0 plus a. And now we remember that delta t is, in fact, t1 minus t0. And if you look at this equation, the only unknown here is t1. So we're going to solve algebraically for time 1, then make our numerical substitutions in the last step. So t0 is 0. Let's just substitute that. Okay, so to do the algebra, let's take that v0 to the left side of the equation where it picks up a minus sign. We then have v1 minus v0 equals a times t1. Now I'm going to divide by a in flip sides. That gives me t1 equals v1 minus v0 divided by a. Okay, so now we can substitute our values. v1 is 29.05 meters per second. v0 is 20.11 meters per second. Divide by the acceleration, 3.00 meters per second squared. Okay, so if you plug all the numbers into your calculator, you will get 2.98. Now let's think about the unit. if I look at the numerator, both of the terms in the numerator have units of meters per second. The denominator has units of meters per second squared. So meters cancels meters. And then what remains is 1 over seconds divided by 1 over second squared. Now I can take that second squared, flip it into the numerator. So I then have second squared over seconds for the unit of the answer. Second squared over seconds is seconds. So I get time 1 equals 2.98 seconds. And indeed, seconds is the unit I would expect for the time. Okay, so make sure in any of the homework problems that you do, solve symbolically first, then make substitutions of numbers along with units. And when you calculate the numerical value of the answer, you calculate the unit as well. Now we're going to solve for the distance that the car traveled as it was increasing its speed from 45 miles per hour to 65 miles per hour. In other words, we are looking here for x1. So go through these equations and see if you can find an equation that has an x1 in it and all of the other quantities are known. So if you find such an equation, solve for x1 symbolically, then put in numerical values with units, calculate the numerical value of the answer, and calculate the unit of the answer. So go ahead and try that on your own and then rejoin the video. You may have noticed that equation 3 as written is already solved for x1. And we also know all of those quantities on the right side of the equation. So we can go ahead and take equation 3 there and just make our substitutions. Now here's our solution for part B. We have x1 equals, I'll just copy it, x0 plus v0 delta t plus 1/2 a delta t squared. Now x0 is 0. Everything else we have to substitute. Okay, so v0 was 20.11 meters per second. Delta t from time equals 0 to time equals 2.98 seconds would be 2.98 seconds. And plus 1/2, we substitute the acceleration, which is 3.00 meters per second squared. Then we substitute the time interval, which is 2.98 seconds, and then squared. Okay, now put this into your calculator, and the numerical value which comes out will be 73.2, but we also want to make sure that the unit came out right. So look at the first term. You have meters per second times seconds, so seconds cancel. Now look at the second term. You have meters per second squared, and then here we have units of seconds squared because the unit is squared along with the numerical value. So we have meters per second squared times seconds squareds cancel. So the unit of the second term is also meters. So here the unit is meters, here the unit is meters. So the unit of the answer is meters. And we have that the car traveled 73.2 meters as it was increasing its speed from 45 miles per hour to 65 miles per hour. And now we have solved our first problem involving an object moving with a constant acceleration.